Good morning, everybody. We'll get started in just a few. Give me just a few and we'll get started. Thanks for your patience. All right. Good morning, everybody. Thanks for joining in today. Let me go and share my screen. So are you seeing the course homepage okay? Anybody can? Okay. Thank you.
Yes.
Thank you. All right. Let me get into the weekly overviews. Okay. So on Thursday, I will start talking about the project again. But today I want to get into the material on momentum. I'll do my best to go through that, and I'll probably have an opportunity to start the material on work and energy. Whatever I don't finish on that today, I will do on Thursday, in addition to talking about the project and looking at some example problems related to both of those topic areas. All right. So you can see from the objectives, the kinds of things we'll be looking at in this material as far as momentum goes right now. We're gonna, of course, we wanna learn what is momentum and its counterpart, impulse. We'll learn how to use the definitions and the formulas to do some calculations. We'll look at the law of conservation of momentum, and we'll look at its usefulness in helping us to understand collisions. And then, of course, we always solve problems related to these topic areas. So that's what we're going to get into here. As a reminder, you have some items due by Saturday. The discussion on momentum and problem set 8. Problem set 8 is on gravitation from last week. And you see you have another bonus that you can do. And if I have enough time today, I'll get into talking about that second bonus. So here are the materials for the momentum overview. Chapter 7 in your textbook deals with momentum. So you can review that. And there are some videos I even bookmarked a simulator, if I'm not mistaken, is visualizing collisions as a simulator. And that will be helpful to you because those of you who will see me in lab later on today, we'll be talking about that actual simulator. All right, bear with me for a moment. Let me turn this down. All right, so here we are in the momentum notes. Okay. And so now you see here, it says linear momentum. And that is because we're looking at momentum for an object that's moving in a straight line. Okay, there is a property called angular momentum for an object that's rotating or moving in a circle. But we don't focus on angular momentum, okay? And a lot of times you hear linear momentum just referred to as momentum, all right? They don't always say linear momentum, but if they do, you know that they're talking about momentum. Now, the question is, how do we define momentum and what is it actually? So I always like to define momentum as the amount of motion. So momentum helps us to measure the amount of motion that an object possesses. And the way we measure that is by looking at the object's mass and the object's velocity. And we take those two properties that we can measure mass, we can measure velocity, and we multiply them together. And we get this property called momentum when we multiply mass times velocity. And we use the letter or the symbol P to represent momentum, lowercase p, okay? And it's a vector because velocity is a vector, right? And so momentum will be in the same direction as velocity because velocity is the part of momentum that is a vector, right? So that's a real easy property to calculate, mass times velocity, okay? That tells us linear momentum or momentum, and it's a measure of how much motion an object possesses. There is a connection between linear momentum and Newton's second law. So what we can do is rewrite Newton's second law using linear momentum, okay? And so what you see in the box is how we can express Newton's second law using linear momentum. Remember, we learned a long time ago that that delta looking symbol, that triangle looking symbol means change. So if we look at the change in momentum divided by the change in time, that is equal to the net force. Well, we also know that net force is equal mass times acceleration. That's Newton's second law. F net equals m times a. But now we see that it's also equal to delta P over delta T. So that means that we can write Newton's second law more than one way. We can write it in terms of acceleration, m times a, or we can write it in terms of the change in momentum, delta P over delta T, okay? So, and you know, while we don't get deeper into the math than what you see written there, it is a pretty powerful statement. And when we solve some problems, I'll take a minute and go a little bit deeper into that connection, okay? But for now, just to introduce it to you, you can write Newton's second law more than one way, okay? Now, what are the units when dealing with momentum, right? Because if it's something that can be measured, then it means it has units. So here we are with a new property, momentum, and here is a new unit in the metric system, kilogram meter per second, Well, if you go back to the definition of momentum, mass times velocity, we can see that the mass will be in kilograms and the velocity will be in meters per second, okay? Kilogram meters per second. Please do not confuse kilogram meters per second with newtons. Newtons is kilogram meters per second squared. Momentum is just kilogram meters per second, mass times velocity, okay? And I like to call impulse momentum's first cousin. You know, first cousins are often close to one another, and you know they share their secrets and they hang out together and those kinds of things. Well, impulse and momentum are kind of related like that, but it's not actually momentum, it's the change in momentum. So if we say change in momentum is equal to F net times delta T. So what they did was, you can see clearly what they did was they multiplied this both sides by delta T. If I multiply F net by delta T, I get F net times delta T. If I multiply this side by delta T, the delta T cancels out and I'm left with change in momentum. So they rewrote this equation for Newton's second law in terms of change in momentum, okay? And that property, change in momentum, is referred to as impulse, okay? Not momentum, change in momentum, okay? So it's a rearrangement of Newton's second law. And so we can say that the impulse, change in momentum, delta P, is equal to the average net force. And we'll see what we mean by that in just a moment. Average net force times the change in time. So if you apply a force for a time period, delta T, you can change an object's momentum, okay? So that they're saying here, you know, how can we interpret this equation? That's what that last sentence is about. It says, the above equation implies that a given impulse, delta P, can be attained by a large force over a short time span or a small force over a longer time span. So if you look at the right side of the formula that's in the box, F net times delta T. Well, what they're saying is sometimes your F net will be big and your delta T will be small, and that will produce a large impulse. Or your F net could be large and your delta T small, and you'll still get a large impulse. So F net and delta T can adjust, you know, vary in terms of the amount, but the product will combine to still give a substantial impulse, change in momentum, okay? And you see that kind of application in real life with things like golf swings or, you know, like tennis when they're hitting the ball with the racket, right? They want to produce a large impulse. And so they have to apply either a substantial force over a short time period or a small force over a large time period, okay? To make a golf swing or a tennis ball or batting, even baseball, batting the ball effective. That impulse is really important in those types of interactions between objects, the bat and the ball, for example. If you want it to travel far, then you have to increase the time span that the bat is in contact with the ball. We call that good follow through. And this is what they're talking about here. You know, they're talking about the average effective force. We don't need to get into that. All we need to know is that if we apply a net force over a time period, we can change an object's impulse. But this is kind of like in reality, because if you think about it, an athlete is not going to hit the ball with the same amount of force every time. And so we look at, okay, on average, what is the force that they apply? conservation of momentum, okay? Now, this is a very important concept because throughout science, you find this idea of things being conserved, okay? And when we say conserved, we don't mean like save the whales conserved, but although that is important, right? What we are talking about in physical science and physics and other sciences areas where you run into this idea of something being conserved means that the amount you have remains constant, okay? So when you can isolate a system, meaning you can protect it from outside forces, right? So when you isolate a system, meaning you almost take whatever objects you're dealing with and put them in a bubble so that no outside forces can interfere, or where your net force is zero, then in that particular instance, you can say that this property momentum is conserved, meaning the amount of momentum you have in that closed-in system is constant, okay? And so what we do is to express this idea of conservation of momentum in terms of a formula, right? Because, you know, in physics, that's what we're shooting for, right? We want to know how we can express this property mathematically. So when we look at this idea of momentum conservation, we look at the total momentum. So what we say is the total momentum in the system is fixed, okay? Now, we can have many objects in our system moving around, but when we look at the total momentum in that system, the amount is always the same. You don't lose any momentum, you don't gain any momentum. The total of all your isolated objects. Imagine, for example, that you're playing pool like 8-ball in the corner pocket pool, okay? And so you'll have all these balls moving around. But if you treat that whole, you know, pool table as your closed-in system, and you take the momentum of each of those balls and add it up together, at any time, at any given moment, you'll get the same amount of momentum every time, the total amount, okay? Each object's momentum can change, but the total is what stays fixed, okay? And here they're talking about the idea of utilizing momentum because it's very helpful when we want to analyze collision motion. Now they're talking about, you know, this kind of recoil collision between, you know, a macroscopic object like quarks and what have you, subatomic particles. We're not getting into that, right? But the idea is that when you want to analyze the motion of objects that are bumping into each other, colliding, momentum conservation is very useful for that, okay? Now, for us to utilize momentum conservation to solve problems relating to collisions, we have to know what types of collisions we're dealing with, okay? So the first type of collision that we'll look at is called an elastic collision. So an elastic collision, now think about this word elastic, stretchable, right? You kind of think of that kind of thing. Well, what we mean when we say elastic in this sense is that the objects will bounce off of each other. So they will hit each other and bounce off of each other, elastic collision. So an elastic collision, momentum is conserved. The objects bounce off of each other. And then they mention this property here, kinetic energy. This kinetic energy is also conserved. Now, we don't need to know what kinetic energy is right at this moment, but this kinetic energy, whatever it is conserved. So when you're dealing with an elastic collision, you must meet 3 conditions. Momentum is conserved, the objects bounce off of each other, and kinetic energy is conserved, okay? Now, the good news for you is we don't really solve problems dealing with elastic collisions because they get a little bit difficult mathematically. Since you have 2 things that are conserved, momentum and kinetic energy, you have to deal with 2 different sets of equations. We're not going there, but you do need to understand what is an elastic collision, okay? And they're showing you a picture here of elastic collisions in one dimension. And honestly, the only types of collisions we can analyze, elastic or otherwise, would be one-dimensional collisions. We don't do two-dimensional or three-dimensional collisions, okay? So what they're showing here in the picture, and remember, we're not trying to get at the math. We're just trying to understand conceptually what's happening here, right? So you have those two objects, M1 and M2, they bump into each other, and then they rebound. You can see they start off, they are both moving to the right. You know that because of the green velocity vector arrows, right? They're moving to the right. They hit each other, and then you see that afterwards, they're moving opposite directions from each other because the green arrows are pointing opposite directions, right? So they bumped into each other and rebounded off of each other, kind of like, right? Okay, and so that's an example of an elastic collision. All right, and I know that you see that it looks like an egg-shaped oval line drawn around. That's how we're isolating our system. No outside forces can get in, namely friction. That's why they call it, they're saying it's a frictionless surface, right? Because you can't have friction in this, otherwise, you know, we can't talk about momentum being conserved, right? But when we isolate the system and there are no net forces going on, the net force is zero, then the amount of momentum in our system before the collision is equal to the amount of momentum in our system after the collision, okay? So we look at these objects, we isolate them, and we look at them before the collision happens, and we figure out their momentum total. And then when we look at this system after the collision, we know that we're going to get the same total amount of momentum, because momentum is conserved. And if it's elastic, kinetic energy is also conserved, and the objects are going to rebound. Now, the kind of collision that we will solve problems with, and we'll look at that on Thursday, relates to an inelastic collision, okay? So in inelastic collision, the kinetic energy is not conserved. Momentum is conserved, kinetic energy is not conserved. And then we're gonna focus on a perfectly inelastic collision when we problem solve, because it's easier because the objects stick together. So these two objects, they collide with each other and they stick together, okay? So momentum is conserved. If we look at these two objects before they collide and after they collide, the momentum total is the same. But the kinetic energy will be different because it's not conserved. And also the objects will be stuck together, perfectly inelastic collision. Now we'll see when we problem solve, that gives us some things we can work with that make the problem solving a bit easier, okay? So, you know, they give you an example down there, you know, like sports. Well, understanding momentum and momentum conservation and elastic and inelastic collisions is like a really big part of like sports, right? That's how they were able to begin to develop protective gear by understanding this whole idea of collisions. So here's an example of a perfectly inelastic collision in one dimension. So you can see we got our objects in a bubble. No outside forces can get in. It's frictionless. Net force is zero. We look at these objects before the collision. You see they're headed toward each other, right? If we look at the total momentum in this system before the collision, we add up the momentum for object 1 and the momentum from object 2, and we get a total, in this case, 0, okay? Let's look at these objects after they collide. Well, you can see after they collide, they're stuck together. They're no longer separate. But the total momentum after is still 0. Why? Because the momentum is being conserved. But look at, in the beginning, our kinetic energy is mv squared. Don't worry about how they got that. But the thing is, if you look after the collision, the objects are stuck together, but the kinetic energy is not mv squared, it's 0. So we know that the kinetic energy is not being conserved because you don't have the same amount before and after. But the momentum, same amount before and after. So a perfectly inelastic collision, momentum is conserved, kinetic energy is not conserved, and the objects stick together. Now, what we have to understand about this collision type, this perfectly inelastic collision, is that because the objects are stuck together afterwards, we have to treat them as one bigger object by adding their masses together. So we'd have to add m plus m after, because they're not two separate objects anymore. So what's the total mass? M plus m. Also, if they are stuck together, they have to move with the same velocity afterwards. Objects can't be stuck together and moving with different velocities. Okay, let me think about an example of that. If you and somebody are walking and you're holding hands, they have to be moving with the same velocity you do, or either they're going to get dragged or you're going to get dragged or something, right? I mean, you have to be moving with the same velocity if you're stuck together, okay? All right, so that's an example of a perfectly inelastic collision. And on Thursday, we'll actually look at some sample problems that deal with momentum in general. We'll look at momentum conservation, and we'll look at impulse, okay? We're not going to these reaction type systems. This reaction type system is what we call the rocket problem. This equation that comes right out of Newton's second law and Newton's third law combined, along with the understanding of momentum conservation, allow us to solve the rocket problem where the mass is changing. We always deal with systems where the mass is fixed. But in the real world, especially for a rocket, since it's burning fuel, its mass is going to be changing. And so you see, when we get to the point where we really understand momentum and collisions and conservation, it does become rocket science, right? So, but we don't do reaction type systems because the type of math that's involved, okay? But, you know, it's not harmful to understand that there are actual systems where the mass is not fixed. And that's the idea of rocket propulsion. Okay. So that's kind of what I wanted to share in terms of background with you regarding momentum. On Thursday, we're going to look at some types of example problems that you will be required to understand regarding momentum, momentum conservation, impulse. And then, of course, you know, we'll talk about your second bonus and that kind of thing, and make sure we cover all the bases here. But I want to go ahead and get into the energy piece of this, because as you just saw, momentum and energy kind of go together, right? So this is the overview that deals with work and energy. And you can see right up top, we're going to talk about this idea of energy being conserved. We'll look at, you know, work and how we calculate work and the appropriate units for all of this stuff. And then, of course, you know, some simple types of calculation. And then finally, we will look at an important property related to energy, and that's power. Okay, and we'll look at the relationship between power, work, energy, and time. Okay. So, you know, for this too, you have some activities. Now, problem set number 9 deals with momentum. Okay. Let me just caution you, problem set number 9 is challenging, and it does take some time. So I would not be waiting until the last minute to get this done. What you should plan on doing is starting problem set number 9. You know, on Thursday, I'm gonna give you some sample problems that'll help you understand what you're seeing in problem set number 9. But I wouldn't wait to get it done because it is a little bit time consuming. Because it's that, you know, when you're using the momentum conservation formulas, it can get a little bit mathematical compared to a lot of things that we've done. Okay, you have a discussion on energy that you have to complete for this topic area as well. Okay, so you have a couple items that are due by Saturday, right? Now, here's material to help you with this, chapters 2 and 8 in the CK12 textbook that you're using. And then there's some energy videos for you, okay? So let me go ahead into this. I'll cover this for you. And then the goal is on Thursday, we'll tie it all together with looking at some example problems and making sure you understand, you know, what you've got on your plate for the weekend. All right. So I think this is a very good way to start off our coverage of work and energy, because those are two terms that we use a lot in everyday life. You know, like I'm going to work, or, you know, I need an energy drink. Now, those are casual ways of talking about these properties, but, and you know, and all that's fine because that's verbiage, right? But we have to be careful because when we get into the physics world, work and energy have specific meanings and specific definitions. Some of you might have had that experience because you might have sent me an article for the project to review that dealt with energy. And I reached back to you and I said, that approach to energy is not relevant for our class, right? While it could be relevant, it's not focusing on work and energy in the way we do in a physics class, right? Because this physical science course is basically an introductory baby algebra based physics course. And so you have to understand work and energy and all of the other properties that we've dealt with and will deal with from a physics perspective, okay? So I always tell students, don't mix up your everyday use of these words with the physics definitions of these words, okay? All right, and so, you know, one of the most important things that we figured out in terms of science is this understanding of energy, because energy permeates every aspect, you know, like biology. You can't talk about biology without talking about things like the Krebs cycle, where you're looking at how the body, human body, or how, you know, living things utilize energy from their surroundings, right? I mean, it's an area that permeates everything, okay? You know, I would dare say a lot of conflict, human conflict, is at its core revolves around this idea of energy, because it's necessary for our survival, right? But, you know, one of the important things from science is that we figured out that there are many different forms of energy, and that these forms of energy are interchangeable. We can take one form of energy and change it so that it's useful in a different way, right? Like you take in food and the body transforms it into energy that's processable and usable by your, you know, by your body systems, right? And our understanding of energy and its different forms and how they interchange is you know, one of the most important contributions that physics has been able to offer to the world. So, work. So if you want to think, just like I said, impulse is kind of like momentum's first cousin. Work is kind of like energy's first cousin. Okay, they hang out together. Work and energy are counterparts of each other. Okay, so that's why we need to understand this idea of work, because we use and transfer energy in a way that we can do work. Okay, so work involves a transfer of energy by a force that causes an object to be displaced. So if you apply a force to an object and that force causes that object to move, you are transferring energy in order to do work, okay? And we use the capital letter W to denote work. please do not confuse this capital letter W for work with the W that we use for weight. Work is a scalar. Weight is a vector. Don't confuse them, okay? So how do we calculate work? How do we figure out how much work this force is doing? So what we do is we multiply the force times the displacement. If we multiply the force that's being applied and the displacement that the object experiences, we can figure out the amount of work that's being done, okay? So now let's, you have to be thoughtful about this because it says here that the force and the displacement have to be in the same direction. So if you're applying a force, the object has to move in the same direction, along the same line as the force in order to do work, okay? And you might be thinking somewhere in your mind, how in the world do you apply a force and the object not move in the same direction, okay? So there are scenarios where you can be applying a force, you can have a displacement, and work is not done, okay? Now we can look at this formula very easily. W equals F times D. If F is 0, obviously you aren't doing any work. If the displacement is 0, you aren't doing any work. So you could be pushing on a wall, and if the wall doesn't move, you aren't doing any work. You applied a force, but there was no displacement. Obviously, if you don't ever push, you can't do work. But what about the scenario where you have F and you have D, but no work is being done? So that's the scenario where you carry an object. If you carry an object, you are supporting its weight with a force. You are moving the object, but the force and the displacement are not in the same direction. So when you carry an object, the work is 0 because the force and the displacement are actually perpendicular to each other, 90-degree angle. When you carry an object, your force is supporting the object vertically. In order to support an object's weight, you have to hold it up against gravity, right? Gravity wants to pull it down, so you have to support that object's weight. So your force has to be vertical to balance out gravity's pull downward. And if you are carrying an object, you don't walk vertically, you walk horizontally. So your force is vertical, but your displacement is horizontal. So they're not in the same direction. So when you carry an object, the work is 0 because the force and the displacement are perpendicular, all right? So now, if we're gonna be looking at work, here's another property already, right? We've come across several properties in this material already. Here's a new one, work. Well, we know the unit for force is the Newton, and we know the unit for displacement is the meter. So when we take a Newton and a meter and we multiply them together, we get this new metric system unit called the joule. The joule is the energy, the unit for work, joule. And the way you get a joule is you multiply 1 Newton times 1 meter. A Newton meter is equal to a joule when we're dealing with work. So be careful, and we'll talk about this a little more when we problem solve on Thursday. When you multiply a Newton times a meter, and you must tell me that it is equivalent to a joule. If you solve a problem for me and you leave it as Newton meter, I'm gonna mark it wrong, okay? Because your units have to be, properly expressed, right? The work energy theorem. So the work energy theorem looks at the relationship between this kinetic energy, 1/2 mv squared, and work. So it says the net amount of work done is equal to the change in kinetic energy. okay? So if we take this property, kinetic energy, 1/2 mv squared, and we look at the final amount of kinetic energy minus the initial amount of kinetic energy. That's what you have in the box. The final is 1/2 mv squared. The initial is 1/2 mv naught squared, right? So we're looking at the change in the kinetic energy. How much kinetic energy did we end up with? Minus how much kinetic energy we started with. That difference is equal to the work done. So you can see from this formula that if an object's speed changes, then we can look at how much work is being done. Okay, work energy theorem. Oh, by the way, they gave us in this work energy theorem the definition of kinetic energy, in case you were looking for it just by itself. Kinetic energy, KE, is 1/2 mv squared. What are the units for kinetic energy? Joules. Why? Because work and energy are related, so they must be in the same unit, joules. Here's another type of energy, gravitational potential energy. So this is the amount of stored energy that an object possesses based on its height. As you lift an object up higher, it stores more energy, gains potential energy. Potential, what does that mean? You know, like when you have potential, it means you can do something, right? You have the ability. Well, when an object stores up gravitational potential energy, what does it have the ability to do? Work. In fact, you'll hear energy defined sometime as the ability to do work. So here, where an object is gaining energy just by being lifted up higher and storing energy, because of the gravitational field, right? So how do we find gravitational potential energy? MGH. That little subscript G tells us gravitational potential energy, and it's reminding us that we're dealing with little g, all right, which is location specific, right? So if you go to the moon and you do MGH and you compare that to MGH, where H's are the same on Earth, you're going to store up more energy on Earth because little g on Earth is bigger. Okay, gravitational potential energy. And again, because this is energy, the unit is joules. So work, kinetic energy, gravitational potential energy are all interchangeable. They're all measured in the same unit, joules. And that's what that's showing in the picture here. You know, as you raise or lower the clock's pendulum bob, right? It's like a grandfather clock where the little thing swings back and forth. But as you raise or lower the chain, at least that's what I think it is. But, as you raise the chain, you store up energy, gravitational potential energy. As you release it, let go of the chain, it releases that same amount of energy. So you raise the chain to store up energy, MGH, and when you release it, that energy, that stored energy gets converted into work, MGH. And that's because gravity is a conservative force. So anytime you're doing work against gravity, storing up energy against gravity, generating potential energy against gravity, that energy is going to be conserved. So the amount of potential energy that you store up is the amount that you have available to do work. And that's because gravity, which is a force, right? Gravity exerts a force. Gravity is what we call a conservative force, meaning the energy that you store up against gravity is always going to be equal to the amount of energy that you can release and utilize to do work. Just to let you guys know, I don't know what the weather is like in your neck of the woods, but in my neck of the woods right now, we're getting some pretty like heavy winds. So, and sometimes when that happens here for me, my power goes out. So if that happens, I'll have to, I'll have to post an announcement of some sort. Hopefully we don't lose power here soon, because it's getting a little bit wicked. But we'll keep going at it until something makes us have to change, right? So now let's look at this idea of this conservative force. Gravity is a conservative force, meaning the work done doesn't depend on where you start and it doesn't depend on the path that you take to do work. It depends only on the start and end points, okay? So when a force is conservative, like gravity, the work done only depends on where you start and where you finish, not how you got there, okay? So gravity is one of those conservative forces, path independent, okay? That's one of the characteristics of a conservative force, okay? And so we can focus on mechanical energy because that relates, that looks at the relationship between kinetic and potential energy, mechanical energy. Some of you sent me articles for the project and I told you, focus on mechanical energy instead. Why? Because mechanical energy is the energy related to motion, mechanics, motion. And when you look at mechanical energy, you focus on kinetic energy and potential energy. And in particular, when you're dealing with gravity or any conservative force, you can say that the sum of your kinetic energy and potential energy is always going to be the same. They're going to be conserved, okay? So at any given moment, the total of your kinetic energy and potential energy is constant. That's what we mean when we say conserve, right? Can't gain any energy, can't lose any energy. The total amount in your system is fixed because you're dealing with a conservative force. And gravity is an example of one, okay? And so you see they took in the box, the last box on the page, they rewrote this conservation of energy by looking at the kinetic energy and potential energy that you start with, the initial, equal to the kinetic energy plus potential energy that you end with, final, okay? So that's a statement of the conservation of mechanical energy. Now, there are non-conservative forces, just like gravity is your conservative force. Friction is an example of a non-conservative force, okay? So the work that would be done by friction would be path dependent. It depends on how you get from start to finish because this force is non-conservative, okay? And when you're dealing with a non-conservative force, you're going to lose some of the energy in the system, typically to heat if it's friction. In this particular case, you'll have this kinetic energy being converted to what we call thermal energy, heat. Thermal energy is a close relative to heat, if you want to think of it that way. So as this player slides and they cover a certain displacement, that friction, always opposes the motion, right? So if the player is sliding to the left, like in this picture, friction force is going to be to the right. But that friction force is path dependent. If he slides along a different path, the friction is going to be different, right? And so it's path dependent. And so in that particular case, energy is not conserved, okay? Because friction is a non-conservative force. And so, if we want to look at, how can we account for this non-conservative, the work done by non-conservative forces, we can rewrite this conservation equation to include the work done by non-conservative force. You can see everything else, KE and PE are the same as before, but we added in this WNC, the work done by non-conservative forces. So that way we can say the total amount of energy that we started with is equal to the total amount of energy that we finished with, right? But if we're dealing with non-conservative forces like friction, we have to add that work done in, okay? And so we can utilize that to help us figure out the amount of work done by a non-conservative force. The work done by a non-conservative force is equal to your change in kinetic energy plus your change in potential energy. Now, honestly, I'm not here to try to make you deal with that equation, but I am interested in you understanding this equation, okay? The conservation of mechanical energy. And so on Thursday, we'll look at some examples. Okay, and this expression that you see here is like a, you know, a more encompassing statement of the law of conservation of energy. So the total energy that you start with, the energy from all of your different sources that you're starting with, add it up, and that equals to the total amount of energy from all your sources that you finish with. Okay, and so in that statement of the conservation of energy, you have all different types of energy, like chemical energy, electrical energy, nuclear energy, thermal energy, all that's built into this much larger expression, mathematical expression of the conservation of energy. Whatever have you using this? No, but you need to understand conceptually that, you know, this idea of conservation of energy is very, very important. And when you're looking at it, you have to account for all the different types of energies that are relevant for your system. Efficiency. So efficiency is a means of looking at how useful is the energy that you put in. So it looks at the ratio of the work that you get out versus the energy that you put in. So you put some energy in, you get some work out. You put some gas in your car goes. But what they're telling you here is in the real world, the work that you get out is never going to be equal to the energy that you put in. So that's always going to be less than 100%. Okay? There's no totally 100% efficient process in the real world. We can see the efficiency of some processes. Okay, so you can see that you know, some different types of activities or devices in terms of their efficiency. Okay, you can see the electric motor is 98% efficient, pretty good, compared to a diesel engine or a gasoline engine or a steam engine. Look at how inefficient they are. And that ought to tell you something about why we're trying to move to more efficient electric cars versus gasoline and diesel. Some of it has to do with the fact that they're just downright wasteful, right? Power. Power is the rate at which work is done. So that word rate means time is involved. And so what are you looking at there? The ratio of work per unit time. That W in that formula is work. Of course, you know by now T is time. So work per unit time. That ratio gives us power. So if you want to know power, you first have to determine how much work was done and then divide that by time. Okay. Now, when you take the joules for work divided by the seconds for time, you get a new unit, the watt. So be careful. So we got W's all through here, right? this W for watt is a unit. The W in the formula is for work. And then please don't confuse that with weight. Okay. So work per unit time. Now, you may be used to hearing a unit in the English system or in this country, horsepower. You know, when they talk about Hemi, the Hemi engine or whatever, horsepower. You know, your people, how many horses that does your engine have or whatever, you know? And that's literally because that unit was determined back in the day based on how powerful the horses were, okay? So if you want to relate that unit, English unit horsepower, to our metric counterpart watts, 1 horsepower is equal to 746 watts, okay? So that's your conversion factor, in other words, if you want to go from one unit to another. But we focus on watts here. And be careful, when you solve problems for me, don't tell me joules per second. Tell me watts, or I'm going to take points, because your unit will be wrong, okay? You know, that unit watt is, you know, you have exposure to that every day when you think about like 100-watt light bulb, okay? That kind of thing. 100-watt light bulb would be 100 joules every second. The 100-watt light bulb uses 100 joules of energy every second. And look at this. I like this this chart, especially for those of you who might be looking, you know, at some types of medical field, interested in the medical field, or, you know, have a need to understand body systems, right? In terms of their energy conversion, right? Right. Look at the brain. In terms of, they call it metabolic rate, BMR, right? So look at the power consumed when at rest. You can see the liver and the spleen are like really, really important organs in terms of the amount of usage of power and their BMR in the human body. You can see the heart, you know, out of all the body organs, the lowest power consumed at rest. You know, it's like when you're stationary, not moving around, not doing things. That's pretty cool to see that kind of information, you know, to think that we have moved to an understanding level to assign these kinds of measurements to various organs in the body. You know, this tells us how the rate at which, you know, these organs are consuming the energy that we get through food, right? And then this last one, well, there are a couple of ones left, talking about the energy use in the world. You know, right now we're paying what, a little over $4 a gallon? This kind of stuff means something when you start thinking about that, your pocketbook, right? So look at the level of energy consumption and how it's projected based on, you know, data and analysis that have been done. Morning. All right, so, you know, it looks at the power consumption in different countries, excuse me. And any surprises there? No surprises to me. And we're right up there in terms of our use of power, right? Remember, power is directly connected to the amount of energy that you're utilizing, because work and energy are interchangeable. All right, so that's what I wanted to cover with you this morning. I'll stop sharing. If you have questions, feel free to unmute and ask your question. Otherwise, we'll get back together on Thursday. We'll do look at some sample problems. I'll talk about your second bonus. Make sure you're, you know, we'll talk about the project a little bit. So we'll have quite a few things on our plate on Thursday. But, you know, we'll get through it and make sure you have what you need. Are there any questions or anything I'll cover today? Osaya? Iso? Any questions?
No, ma'am.
All right. Have a great day. Y'all stay safe and whatever this weather turns out to be.
You too.